This is the second part of our video in section 5.3. We're looking at angle bisectors of a triangle. So here is a triangle, and what we're going to do is we are going to make sure that this red segment is an angle bisector of this angle. And we're going to come down here to this angle, and we're going to do the same thing. We're going to make sure that the red segment is an angle bisector. Now, these angles obviously don't have to match those, but these need to match each other to be an angle bisector. Same thing with this angle over here. Now, just like we saw in previous sections, these red segments that are angle bisectors, they're concurrent. They're going to touch at this point P. And here's the neat thing about this. When these angle bisectors touch, this point P is a very special point. This is the point that is equidistant from each side. Even though it doesn't look like it, I tried my best to make this work in PowerPoint, but the idea is this distance on a right angle to this side matches this distance on a right angle to this side. And it matches that one as well. So the blue segments are the same length. The red segments don't have to be, but the blue segments must be. This is theorem 5.7. It's called the concurrency of angle bisectors of a triangle. That point of concurrency of all three angle bisectors of a triangle, that's called the incenter of the triangle. The incenter always lies inside the triangle. Because the incenter P, we'll call this P here, is equidistant from the three sides of the triangle, a circle drawn using P as the center and the distance to one side, that would be the radius of the circle. That doesn't really look like a right angle, but I tried. So you can see how this shows you that these are all equal because they're all a radius of this circle. They're saying that this circle is inscribed within the triangle because this circle is only touching this side in that one place right there. Now, as it comes along here, it's going to touch this side in one place, and it's going to touch this side in one place. So that's called the incenter. So we're going to use the concurrency of angle bisectors. In the diagram, N is the incenter. That's important that you know what an incenter is, because that's telling you that these angles all match. The incenter is where the angle bisectors come together. So these must be angle bisectors. And notice how they don't have to be the same length. This one is definitely appears longer than this one and this one. But the thing that the incenter does is it creates congruent segments here along these blue segments. As long as you have right angles here, this point is the same distance to this side as it is to this side and as it is to that side. Okay, so we need to find the distance from N to D, F to N, and N to E. And we don't know any of those distances. But notice how inside this triangle with that incenter and these angle bisectors, you have right triangles that are formed. So I'm going to redraw this right triangle. We have a leg of 16 and a hypotenuse of 20. How can you find this other leg? I know triples. If you don't know triples, you can still do this as well. But a very common triple is 3, 4, 5. If you multiply them all by 4, you're going to get 12, 16, 20. And notice how that helps you. The two biggest sides on this right triangle are 16 and 20, so your smaller side is 12. If you weren't a triples person and you didn't recognize that, then you need to take the square root of 20 squared minus 16 squared, and it's going to give you the same answer, 12. So if this piece is 12, how long are these other blue pieces? They're 12 as well.